All right. So again, watching the video notes if you're absent is a huge part of understanding what we're talking about. So make sure if you are ever absent, you not only get the notes filled in that we did, but you watch the video notes so that you can get everything that we talked about. So yesterday we said that our ideas and our understanding of things change. Okay, so we're going to look a little bit today about how the atom itself has changed and kind of, as we get more information, how we've kind of adjusted our thinking on things. Right, so something that that I took away from the Bill Nye is when he's like talking about like the alphabet, and you have 26 letters, and those letters combine to make words, and then those words combine, you can make sentences, and those sentences can combine, you can make paragraphs, and then, so it keeps getting bigger and bigger, right? And so the atom is the smallest part. So when you put atoms together, you get these things that we call molecules, right? And so just like letters going together make our words, small pieces are the atoms that can come together to make molecules. So that's a really nice way to think of it. Because the atom is the smallest part of an element that retains the chemical and physical characteristics or properties of that specific element. If you make a change to some of those properties, then you change the element that you're dealing with. And so that's going to be a big focus, right? And so obviously this is the atom. This is kind of the model that we use. I heard somebody, I can't remember if it was in here, I think it was, saying, oh, Jimmy Neutron, right? This is kind of like, if you remember the cartoon Jimmy Neutron, it always had like the picture similar to this of like little cartoon atom. Where we have our nucleus, and then outside it we have the electrons kind of buzzing around. All right, and so we are on slide number 5 now. And so the atom has 2 measurable properties that we're really going to be focusing on this year. And so those are the mass, which is probably something that you're familiar with, right? Mass is how much matter is in something. And then its charge. Is it positive or is it negative? And so we had some things in 8th grade science that should kind of help you think. If you think back, we talked a lot about electrical charge with that positive and negative, and we also talked with magnetism, kind of the idea of polarity, where it kind of acts as like a positive and a negative as well. So we're kind of used to this idea of charge. Excuse me. And so when we're talking charge, and this was kind of that property that was a little bit hard. A lot of times people struggle with trying to identify what a charge is, but it comes down to having an unbalanced number of protons and electrons, right? So if you have 5 protons and 5 electrons, they cancel, right? Every positive has a negative and they cancel each other out, so the atom would be neutral. If you have even 1 more proton than you do electron, or 1 more electron than you do proton, that would be technically considered charged. Now, the more unbalanced it is, the more of a charge it has. And so we did talk about that quite a bit last year at the beginning of the year. But unbalanced protons and electrons is going to be a key and a big part of this to remember. Okay, and again, if I go too fast or you miss a blank, ask somebody next to you or back me up. Sometimes they get click happy, so just let me know. All right, this is all straight up review. You should most definitely remember this. So the proton and the neutrons are here in the nucleus. The protons have a positive charge. What else, what kind of charge do the neutrons have that are in the nucleus as well? What charge do neutrons have? Neutron. Neutral, or no charge. And then the electrons, which are buzzing around outside the nucleus, these little orbits kind of are like showing that it's kind of like 3-dimensional, where the electrons are kind of like going all around. What charge do the electrons have? Elijah? Negative. Very good. See, I told you guys knew this. I just couldn't remember what came next, neutrons or electrons. Okay, neutrons are no charge in the nucleus, and then electrons are negative outside. Okay. And it is nice because a lot of our 8th grade topics kind of go into our physical science stuff. And because of that, you know, a lot of this is a little bit familiar, which is nice, so it's not like it's totally brand new concepts. We're just gonna add to it quite a bit this year. Okay, and again, the electrons are outside. And if you remember that part of the Bill Nye yesterday where the sound went out, and it showed like that little vibrating kind of, looks like a little rubber ball kind of shaking, and then he ran the 500 meters, that's to signify how far away the nucleus is from where you find the electron. So you have all this open space between the nucleus and where you would find the electrons. Okay, so the nucleus is found in the center of the atom, and it is made of the protons and neutrons. A lot of times I'm going to just use a P and an N for proton and neutron, and that's going to be something that you're definitely going to need to know what is found in the nucleus. All right, which two of those subatomic particles? It is only a very, very, very small fraction of the overall space that an atom takes up. But just like the Bill Nye showed, it's very concentrated, very dense, and it actually has the biggest mass, or the most mass of the entire atom is found right there in that nucleus. It's so much of the mass that they say almost all. Okay, really, the electrons just take up a very, very, very small portion, or 1/2000th of the total mass is for the electrons. So 2,000 times more mass is found in the nucleus than in the rest of the whole atom. So that's pretty extreme, right? So that's kind of the picture that you have in your mind, this very concentrated, this very dense nucleus, and then from that, you have all this open space, and then the electrons kind of buzzing around outside. Pretty straightforward so far? Okay. All right, so now to the electrons. They are found orbiting around the outside of the nucleus, and these different, there's kind of different views of it. Sometimes they show them kind of like this, where it looks like reminds me like of a dartboard, where you have like the concentric circles. Here it's showing kind of a more realistic, kind of three-dimensional, where they have an orbit, and this one's going this way, and these are going this way, and these are kind of going this way, kind of showing you know, different arrangements, but both of them are showing that they are separated from the nucleus and that there is open space. Now, obviously, is it practical to make the nucleus here and then start the circles way out here? Not exactly. We realize that in real life there's actually a bigger gap than what we usually see in most of our models. But it's just kind of more practical to show them like this than to show the nucleus and then have a bunch of open space and then show the electrons in their orbits. So sometimes they're called orbits, sometimes they're called electron levels. But it makes sense because an atom can actually gain or lose electrons. And if they're found on the outside, it makes sense that that's going to be the subatomic particle that can be removed or added, because it's on the outside. It'd be harder to change the nucleus because it's on the inside. So like if you have like a mass of people, okay, let's say everybody in here gets in a big group. If you're playing a game and like you're trying to like steal people, it'd be easier to steal somebody from the outside of the big group than to try to like get your way in and get somebody from the inside. Agreed? Same thing if you're trying to like add somebody to the group. If it's easier to like throw them to the outside than to try to like push them and get them into the inside. And so that's the same thing that happens here. These electrons that are at the outermost are the ones that can be taken, or the ones that, the location where maybe electrons will go. And we'll talk a lot more about that here later. But it's the electrons that can be exchanged. So if an atom takes on electrons, if they gain electrons, we just said electrons have a negative charge. So if you are gaining negatives, it gives the atom an overall negative charge. So even though you're gaining, and gaining you usually think as a positive thing, if you're gaining negatives, you're giving it an overall negative charge. Opposite is also true. If you have an atom losing electrons, well, losing a lot of times we think of as a negative. Well, here, if you're losing negatives, you're losing those negatives, meaning now that you have more positives. And so it gives it an overall positive charge. And so this is going to be important as we start looking at the arrangement of the periodic table. But gaining electrons actually makes the atom overall negative. Losing electrons makes it overall positive. And so a lot of times this year, there's going to be things that I'm going to say, hey, don't memorize that. And you're like, what? Then why are we learning this if I'm not supposed to memorize it? I want you to learn it, but I don't want you to memorize it. If you start to try to memorize some of this stuff, it gets really confusing. Gain, lose, positive, negative, blah. Like it gets all jumbled up. Try to think logically, right? And if you just think about things and can reason it out, then there's no extra like memory that you have to like jam in your brain. Like it's just thinking of it logically. Like, okay, you have gained electrons which are negative. So yeah, you're gonna have this atom now be negative. Or if you think, hey, I'm losing negatives, well now you have more positives, making it overall positive. So just try to logically kind of talk yourself through it instead of memorizing it. And as we get to different things like that throughout this year, I'll try to be very clear, because there are things where I know when people try to memorize them, they get them switched, and it's easy to get things confused. And this is definitely one of them. So here's where we're going to get to look at the different types of models and how our thinking has changed over the years on what the atom is and what the arrangement is and things like that. I believe, we'll come back to that in a minute. You don't start picking up with your notes again until slide like 19. So we're gonna do slide 10, and then I just think it's good for you to kind of have a little bit of background knowledge. I'm not going to test you on all these different models. We could spend a whole unit on just those. But I think it's important to realize like what we know now is not what we have always believed with the atom. Kind of going back to that idea of yesterday, that ideas change, right? So we have 6 important changes. So the first one is the very first idea of the atom came from Democritus, and we'll get into these in more detail. And then John Dalton came up with some additions, J.J. Thomson, Ernest Rutherford, Niels Bohr, and then finally where we are today, which is called the electron cloud model. And so these are kind of, this is kind of the progression of how we have gotten to where we are today with our understanding of the atom. Okay, and again, this is just kind of some background information. So, in 400 BC, Democritus proposed that atoms make up all objects. This was revolutionary, like that there's one thing that is responsible for everything that we have in our universe, right? It's kind of like, oh, really? Like everything seems pretty different. And so this was kind of a big, huge, renowned idea. He also proposed that these atoms, these things that make up everything, are solid spheres. So he was kind of right, like atoms are not solid, but they are represented as kind of a spherical shape. And so he's the one that came up with this word, and Bill Nye said it too, the atom means indivisible. Atomos is actually the Greek word, and so it means it cannot be cut or divided anymore. And he showed that yesterday with cutting the cheese, right, where he kept cutting, until, showing it can't cut it anymore. And so that is when you get to that smallest base of that element of the atom, that's as far as you can get it to be cut without changing its physical chemical properties. So now we're into the 1800s with John Dalton, and he proposed something called the atomic theory. And so it says all substances are made of atoms that cannot be created or destroyed, and atoms of the same element are exactly alike. This was a huge idea, that there are different types of atoms, and that atoms of a certain type are all the same. And that is true. That is something that we still hold on to today. And so it says atoms combine in whole number ratios or proportions to form compounds. So this is also a huge idea. So when we start looking at chemical formulas, like water is H2O, that little 2 means 2 hydrogens to every 1 oxygen. That is a set proportion or ratio, a 2-to-1 ratio. If we're talking hydrogen peroxide, H2O2, it's 2 hydrogens to every 2 oxygens, right? And so that combination is important. So not just that you have hydrogens and oxygens, but in what proportion are they combined, okay? And those set proportions make them very unique compounds that are formed. Water is not the same as hydrogen peroxide just because it has that 1 extra oxygen for every molecule. And then in chemical reactions, atoms are combined, separated, or rearranged. So he really was on to something, okay? He didn't have all the specifics, but he was on the right track, which again, very impressive. You know, considering the equipment and the tools that he had available to figure some of this out, or at least theorize it. He wasn't sure it was exactly true, but that was his thoughts. So now we have J.J. Thomson in 1904, so close to, you know, close to 100 years later. He was doing some experiments with electricity, and he discovered that there are some negative parts of the atom. And so we'll look at cathode rays a little bit more, can't remember what day, here soon. But basically it's putting electric current and it can separate out the electrons in different gases. But he was able to realize that there's some negative components to these atoms. Okay, so he came up with something called the plum pudding model. We know, or he knew at that time, that atoms are neutral, meaning that, you know, there's an equal number of positives for an equal number of negatives, and so they cancel each other out. So if you have a negative component, you have to have a positive component to the atom as well. And that's just kind of like working backwards and deducing. A negative means there has to be a positive if it's overall neutral. Okay? And that was kind of his big contribution. But he called this the plum pudding. Anybody ever had plum pudding? It's like some kind of pudding that has like either dates or raisins in it. I think it's more like an old-fashioned kind of like British type dessert. But this is supposed to be the pudding, and then the electrons are the plums. So he wasn't accurate about how the electrons were arranged, but he was accurate realizing that there are negative components to the atom, and they are in there with some positive components. So he wasn't quite right on the arrangement, but still good contribution. And then, okay, so this is one of the cathode rays that he used. And so when electricity was discovered, you know, they were able to use electricity in different experiments now. And so they were able to push gases through this tubing system and excite them, and then they're able to basically separate out some of the electrons, and it's able to even cause some of the different gases to glow, which is one of the properties of certain types of gases. So that's kind of how he got started. And so basically, you know, it's moving from one of the positive ends, which is the cathode end, to the anode end, back and forth between the positive and the negative, and seeing that there is that negative component to the atom. Okay, again, showing it here as well. Okay, and so they were able to see, you know, the reaction of the cathodes and how they reacted to the magnetic fields and how they reacted to that electric current being pushed through them. All right. I'm going to keep going. So sometimes with you guys, I apologize. Because I don't like to keep starting and stopping my video notes. So I'm gonna go all the way through the notes and then we'll backtrack to the videos. So, you know, sometimes it's a little out of order. It's still good, but just a little bit different. So just bear with me on that. I appreciate you guys being my first class, letting me videotape in here. So now Ernest Rutherford, he was actually a student of J.J. Thomson's, and so he was involved with, you know, using electricity as well. But he performed something called the gold foil experiment. Okay, and this is kind of a big idea, so our notes do kind of pick up here again. So he took gold foil. So, you know, like, I think it's like extra gum that if you peel the green or that blue foil from the paper, it's that real, do you have it? Yeah. So a lot of times people will do that, like or I guess silver, like you can separate that foil from the paper on that stick of gum. Okay, I see people do that quite a bit. That's what I think, even thinner than that, but it was gold. All right, so solid gold molecules in this really, really, really thin sheet, okay? And he shot alpha particles, which are positively charged particles, at this gold foil. Most of the particles went right on through. Okay, but randomly, those alpha particles were kicked back or reflected back to this screen where it picked up the alpha particles touching it. So it picks it up here as they go through, and you would think they all should just go right on through, but you see there were some randoms shooting around. Okay, they were deflected at an angle, a few of them. So it made him ask, why are they not all going through? Why are some being deflected? What is happening? Okay. And so, again, seeing the alpha particles being shot through, most of them hitting, some of them bouncing, what's going on there? What is the deal? And so from this experiment, he learned a couple things. That the atom is mostly empty space, because as those positive particles go through the gold foil, most of the time they were able to go right between the nucleus and the electrons. Right? So they were able just to slide right on through. Right? That is a huge idea. It basically is like saying, hey, the atom is not solid. If it was solid, then none of the alpha particles would get through. It's also let us realize that the nucleus is very dense and very, very tightly packed. If the nucleus was not dense, it would allow those alpha particles to go through it as well. But it's like it was hitting like a solid mass, and so as the alpha particle would hit that, it reflected a few of them. Most of the time, you know, it was missing the nucleus as those alpha particles were going through, and that's why that's why most of them went through, because the alpha particles missed the nucleus. But if it hit the nucleus dead on, then it would be deflected or reflected off of it and bounce back. Now, what would make a positive alpha particle repel? What charged item? A positive item would cause a positive alpha to repel, to move away. And that's exactly what happens. So if it hits a positive, it bounces it back. If it hits a positive, it bounces it back. And so that's the third piece of information that came from this, that the nucleus has to be positively charged. And we're like, duh, we know all that. Well, we know it all because of him, right? So this was a huge idea. And so I just like to show, you know, kind of that contribution. Let's look at Niels Bohr here. So he hypothesized that electrons travel in orbits or energy levels around the nucleus. Okay, so here's our nucleus, again, very tightly packed. Protons and neutrons, positively charged, because if you have protons and protons are positive and neutrons have no charge, then this has to be positive. And then he says all the electrons are out here. Energy levels forming around the nucleus. Okay, and so this is a very simplified version, and if you take chemistry with Ms. Durkee as a junior, you will look at this in a little bit more detail, but this is kind of a model that we still use today because it's very simplistic. It helps us to kind of visualize and use this, you know, if we need to figure out the electrons and how they're reacting and how they're changing. So this is a model that we still use today. Now, what we think is really happening is that they're not in these perfect little circles, these perfect little tracks, these perfect little lanes around the nucleus. What we are kind of at now is something known as the electron cloud model, where the electrons travel in these areas instead of levels or like perfect circles. So they're kind of in a location, but not a fixed lane. So it's a little bit more relaxed. It's not as rigid as, okay, they have to be here and then here and then here and then here, like the lanes on a track, or like Niels Bohr, where it's like, okay, they have to stay right here. It'd be more this area than this exact like lane or orbit. Okay. Okay, so I'm gonna stop with the notes there, and we're gonna have a few videos here. Start with the